For those attendees who wanted to have the information on the DGX-1, I will now start with that presentation. That presentation has not finished. It will start now. Okay, DGX-1. What are we talking about here? Okay, I'll skip the marketing slides so that we get to the nitty-gritty. Okay, deep learning. We already had a slide going in this direction. Speech recognition, robotics, and that press release, which caused a major uproar. The world champion in Go was beaten by an artificial intelligence, and this was what is causing a major uproar. After this, the Southern Korean government announced that they would now finance deep learning within Southern Korean universities with hundreds of millions of euros. So it did have a major effect. They're not going to sit back and have a computer beat their own world champion in Go. So, as I already mentioned before within the Tesla presentation, this is the way it was done in the past. Hand-coded, hard-coded. You had experts on a specific task generating expertise in functions doing specific roles. In terms of computer vision, for example, in terms of analyzing 2D images, that would have been functions, for example, capable of detecting edges, detecting lines, detecting color changes within images, etc. So yeah, you had low-level functions doing a specific role. In terms of speech, for example, the normal way of doing it would have been taking the raw wave form, doing a FFT, doing a frequency translation, doing separating the speech into various frequency bands, then extracting speech features, for example, like phonemes, trinames, things like that, and then building from these low-level features, you would then have a representation of your speech or your language. That is actually the way they've been doing it for 20 or 30, 40 years now. But nowadays, it is possible of feeding the raw waveform right into a neural network and getting better results and faster results at the end. Doing speech detection, speech translation, speaker detection is a topic at the moment. Your speech, the way you speak, is similar like the fingerprints of your hand. The fingerprints of your hand will represent who you are. The way you speak, irrelevant if you have a cold or not, doesn't matter. The way you speak your language is like a fingerprint. And that's why companies like PayPal, etc., are looking at ways of being able to do speaker detection based on the speech you are giving them in terms of talking to your mobile phone, talking on your standard delivering the speech to that computing side is sufficient to be able to recognize who you are. So you don't have to do any pins, tons, whatever. You will be the speech will be representing your person. And they do that at a very high accuracy level. They can even detect in which mood you are. They can detect if you're angry or not. And they can do that on very subtle levels also. And this is also of interest, for example, for call centers. Call centers do the same thing. If you call a call center, then the best information for the person who is accepting your call They would like to have information, in what mood are you? And then if they have that information at hand, they can deal with your case better. They can handle you properly. And so we have a lot of companies who are looking into ways of extracting additional non-speech information from the speech you are delivering. Okay, but former times, everything done in hard-coded. If it's not done in hard-coded and that feature is not coded, it will not be recognized. Simple thing. Nowadays, you don't code a single line of code anymore. The magic relies on two things: generating or designing a neural net of your choice, which fits to your problem, of course. So that's where you need the domain experts again. You still need domain experts to know what you're looking for, to know what you would like to differentiate. So the domain experts will be needed for a correct design of a neural net. But we have a lot of neural nets, pre-designed neural nets out there you can use. So if you're into detecting objects within an image, you're probably using an AlexNet or an AlexNet, which you have maybe modified a little bit. But everything will boil down to an AlexNet if you're doing object detection in 2D images. It's as simple as that. We have a lot of neural net designs which have been specifically designed towards a specific task, and they have shown that they have outstanding performance in this field. Then the second thing is, okay, neural net doesn't have any expertise at all. It's dumb like a newborn child. It has to be trained. It will be trained with millions and billions of tagged data sets to train the network. And that's actually what we're doing nowadays in terms of deep learning. So a deep learning scientist doesn't code anymore. He uses a framework of choice. Okay, if he wants to use it in an inference phase, he will have to interact with some other software, so we'll have to be defining software APIs, etc. He's not going to use a standard Café Torch or Theano framework. He has to use that output in some sense. So there'll be some software APIs he'll be using for the overlying software, of course. But in terms of deep learning, he's not reinventing the wheel. He's using existing frameworks. He's using existing algorithms. He may do it differently. We know there are a lot of different neural networks out there. So you have convolutional neural networks, you have RNNs, you have LSTMs. Every neural network has its advantages and disadvantages and can be used in a specific way of solving problems. But that's a different story. Okay, as I already said, what actually happens here is after it's trained, that network can, for example, not only recognize the objects within an image. What he recognizes here is this is a little girl, this is a piece of cake, but he also recognizes the interaction of the objects within an image. So what he can actually extract from this image is then, this is a picture of a little girl eating a piece of cake. And it even continues. You can even do a sentiment analysis nowadays. For example, a picture of a dog can be much different. So one picture of a dog can be much different than another picture of a dog. If you have a little cute dog, it's a cute dog. But if you have a Doberman fletching his teeth, that is a different message of this picture. So if you could have an adjective with adhering to the object which is recognized within the image, that totally changes the picture. So you can then be able to differentiate a cute dog from an angry or vicious dog, for example. So sentiment analysis is the next thing the researchers are looking into. And it can be done very efficiently with neural nets too. Okay, looking back at the ImageNet competition, up to 2011, they were using standard hand-coded algorithms, no deep learning algorithms introduced. In 2011, a team from the University of Toronto used GPUs for the first time, accelerating their deep learning approach. And they were able to significantly reach a higher accuracy. So the error rate was much lower. In the former years, they were only gradually improving the performance, but staying at, well, over 25% error rate. 25% error rate is really bad. A human is actually rated with 5% error rate, and that's why we have the line here at 95%. So a human makes about, well, it is rated with 5% error rate. 2011 with 2012, we had huge advances through deploying deep learning algorithms. And in the next years, almost all teams used deep learning in their approaches, and they never used the standard algorithms anymore. So actually, first time using neural nets, trained neural nets, reached far higher levels than the traditional algorithms they were using tens of years before, and now they've all been replaced. So nobody's not using neural nets in object detection within images anymore. And last year, we even reached superhuman performance. So, and that superhuman performance level was actually breached by all three larger contenders. So it was Microsoft, it was Baidu, it was Google. Every one of them reached superhuman performance at the moment. So what we can actually say here now is that within a specific task, we are able to reach superhuman performance deploying deep learning. And that is true. And that is what is driving deep learning at the moment. That's why there's a huge hype at the moment. Who's using it? Well, almost everybody. Almost everybody you see here. And if you take a look at those icons, I think most of you have those icons on the mobile phones also. Irrelevant if it's speech recognition and speech translation being used in Skype. Irrelevant if it's being used by Google, Flickr, Baidu, eBay, Amazon. Everyone's using it for whatever purposes. The purposes, the way they are deploying it can be very different. But everything which is related to predicting future behavior, predicting something in the future based on information I have from the past and from the present, is always a task deep learning is really good at. And we're only at the starting point of a huge opportunity. So deep learning, the deep learning market and the deep learning opportunity will grow exponentially within the next years. That's why we have so many startups and so many companies investing in deep learning. It's very overwhelming. We're right down here, so we have a long way to go, and it's a huge opportunity. To aid that road, to aid proceeding along that road at a higher pace, we've introduced the world's first supercomputer in a box, the world's first deep learning appliance called DGX-1. Don't ask me what DGX stands for, I don't know. Probably nobody knows in our company. Okay, what does this actually consist of? In my last presentation, I was talking about Pascal, our latest architecture. Now, what happens if you take not only one of these, not only two, not only four, but you take 8 of these, and that's what we've done. We've packed eight Pascal GPUs into a single unit. It's a 3-rack rack unit high server. So it fits nicely within each rack. It has a performance of 170 teraflops. 170 teraflops. Okay, to be honest, this is not double precision. This is not single precision. It is half precision. So FP16 performance, half precision. We have 170 teraflops because each Pascal chip is capable of 21.2 teraflops in half precision FP16 performance. Times 8, that's about the number you get. I think we rounded up a little bit, but minor. 170 sounds better than 169.4 or something like that. So it's 170 teraflops. We have 8 Pascal chips in it, each with 16 gigabyte of local GPU memory. We use NVLink and designed it in a hybrid cube mesh. So actually, if you actually think of a cube, a 3-dimensional cube, you place a GPU in each corner, and you think of the edges as being the connections between the GPUs. That would mean you would be using up 3 links per GPU, but we have four NV links per GPU. So what we actually did with the remaining links is, in the top and bottom layer, we did the cross connections, and that's how we constructed our hybrid mesh. So this is based on 5 miracles. I call it 5 miracles. First of all, the optimized Pascal architecture. In my last presentation, I showed you the differences between Pascal and Maxwell. 16 nanometer FinFET technology. So we jumped from 28 nanometer now to 16 nanometer FinFET technology. Our chips are being manufactured by TSMC in Taiwan. Okay, you actually only have a handful of companies capable of doing 16 nanometer technology today. I'll start with the others. It's Global Foundries, which used to be AMD. Global Foundries, which also, for example, here in Germany, in Dresden, they have a manufacturing site. Of course, it's Intel. Intel has manufacturing sites capable of that. IBM has manufacturing sites capable of that. And then it's TSMC, who is our supplier. We do not do that. We do not manufacture our own chips. That risk is too high. Keep that risk to others. Every step further in manufacturing technology is a huge invest in new machinery, in new technologies, and I think the return of invest is very risky. So I'm actually, I think it's a good choice not to invest in that market. Keep it to the other guys who know what they're doing, and there are only a few left. So. Okay, then for the first time, we introduced HBM2. So the memory is actually on die with an interposer layer. So it's actually chip on wafer on substrate. I don't know who introduced that abbreviation. It's weird, but chip on wafer on substrate is what is actually implemented in terms of memory. And we're using HBM2 with 4096 pins, 4096 bits, which allows, of course, for very high bandwidth and very low latency. Then we introduced, of course, NVLink, which replaces what we were using PCI Express for, which actually has 4 to 5 times the performance of PCI Express, and we're working on NVLink 2.0, which will be introduced with Volta, the next generation after Pascal. So we're actually working on reaching higher levels of performance there too. And of course, new AI algorithms. Those are the 5 miracles, which are the prerequisites for the DGX-1. What does the DGX-1 consist of in terms of hardware? Well, this is the hardware. Hope you can see it. It's rather dark. So the main part of the hardware is actually this motherboard with the 8 slots, the SXM slots, which can accept our modules. Here we have the 8 GPUs on top. Then, of course, we have a host system. The host system is this board, this daughter board, which fits into here. It is based on a standard dual socket server solution. It is based on an Intel server solution. So we use 2 E5 processors here, and it's the 20 core version. So we're using rather high-performing CPUs for the host system also. A lot of memory in it, so it comes pre-configured with ½ terabyte of memory, and I think it can be expanded to at least 1 terabyte, if not even larger memory footprint. Then we have power supplies, of course. The thing needs a lot of power. Each of these Pascal GPUs is a 300-watt design. You take 8 of them, then you already have almost 2.5 kilowatts. The host system needs a little bit, so the whole server has a power consumption of around about 3,200 watts, 3.2 kilowatts. You need power supplies for that. They have to be redundant too to keep the performance level up. So it's four power supplies we have there. Then for training, you have to have the fastest possible access to data. Your training data has to be cached, and that's why we've implemented 7 terabytes of SSD cache within this server to be able to cache your training data whilst training. Then for connecting to the outside world, we have 2 standard 10 gigabit Ethernet ports, and if you would like to cluster several DGX-1, you have to have a possibility of doing that too. And that's why we've introduced 4 EDR ports, so 4 EDR InfiniBand ports, each capable of 100 gigabit per second in bandwidth. And that's the way you interconnect several of these. And we have customers using not only 1, but using 2 or 4 of these and clustering them and using them in a cluster for training. In terms of performance, well, last year we introduced a deep learning workstation. This deep learning workstation was a single CPU workstation, and it used actually our highest performing CPU boards at that time. It was the Maxwell-based boards, the Titan X. So we implemented 4 Titan X in this solution. And with these 4 Titan X GPUs, we were able, at the GTC 2015, we were able to train the AlexNet, which is a standard network design. If you train AlexNet for one epoch within the Café framework, that could have been, or that was achieved on this workstation in 25 hours. So last year we needed 25 hours to do that. With DGX-1, okay, I have to be honest, we're using double the amount of GPUs. We're not using 4 GPUs, we're using 8. But that will be a factor of 2. Okay, we're using the newest newest architecture. Okay, that's also true. But now we only need 2 hours. On the DGX-1, the training time for the same task is only 2 hours. 2 hours versus 25 hours. That's a factor of 12.5 in performance within 1 year. If we compare that to what would you need in terms of CPU power to achieve the same thing? The answer is the following. DGX-1 is capable of 170 teraflop. A dual Xeon-based standard dual socket server is actually capable of around about 3 teraflop. It's about 3 teraflop in single position you can reach nowadays. I won't go into detail on the aggregate bandwidth, but this actually tells the story of QPI performance or memory performance versus communication performance via NVLink. So the aggregated bandwidth is 10 times as high. Training the AlexNet, we saw on the DGX-1 2 hours. On this dual Xeon standard server, it would need 150 hours for the same task. Now you could now ask, if I were to achieve the same thing with CPUs, and the limit would be doing that in 2 hours, how many of these dual socket servers would I need to achieve the same task? Okay, then I have to scale in terms of using a higher number of nodes. Problem is with using a higher number of nodes is you do not scale in a linear fashion. If you scale up only by scaling up the number of nodes, then you will be scaling, your scaling will be flat. And that's why, if we say we want the same job done in 2 hours, but with CPU only, you would need about 250 dual socket nodes to achieve the same task. So basically speaking, in terms of deep learning performance. Basically speaking, the DGX-1 replaces 250 standard dual socket nodes. Now just imagine how much space do 250 servers need? How much energy do they need? How many racks do you need to implement this? And how much will they cost? And you need a lot of networking. You have to connect 250 nodes somehow, in some way or another, using InfiniBand or whatever. You need switches, you need racks, you need everything. So you're investing in a large portion of your money into infrastructure which is not delivering any compute power at all. A rack does not deliver compute power. A switch does not deliver compute power. It is the prerequisite for your server to deliver compute power. And taking into account that this solution will actually cost you somewhere around 1.5 to 1.8 million euros, if you compare that to the 130K we're asking for the DGX-1, we're talking of a price reduction of the factor of 10, at least, if not even higher. This is the internals of the DGX-1. Okay, down here you see the two CPUs. The CPUs are connected to PCI Express switch chips because the CPUs themselves do not have a sufficient amount of PCI Express lanes. So we use PCI Express switch chips to interconnect to each GPU because each GPU will be needing 16 lanes. So it's 16 lanes here, 16 lanes here, so you already have 32 lanes here. You need at least 16 lanes for the EDR InfiniBand adapter. And so the only way to do that is using a PCI Express switch chip. So each CPU is connected to 4 GPUs. So we actually have 4 quadruples of GPUs. But they are connected via the standard existing PCI Express technology. The reason is, down here we're using Intel technology and they do not have NVLink implemented. Simple as that. So we use NVLink specifically only for interconnecting the GPUs. So every application scaling multi-GPU wise will have a higher performance due to using InfiniBand. And as I said before, the InfiniBand is used like a hypercube, and you see it on the bottom and top level. We have the cross connections, and then from bottom to top, you only have the edges connected. This is because we are limited to 4 links per GPU. Our next generation Volta will double the amount of double the number of available NV links. So we're going from 4 to 8 there, which will give you the possibility of designing other architectures, for example. Okay, this is a more detailed view. Actually, the most interesting thing here, again, okay, but you see the green lines is the NV link, and each pair of GPUs has then the possibility of going via the PCI Express switch chips to the InfiniBand connectors. So we have four single-port InfiniBand connectors, 1 connected to each pair of GPUs, and that's the way we cluster this solution. And because we are within the same PCI Express root complex, this means that the GPUs can use remote RDMA features, GPU direct features, when communicating from one node to the other. We do not need the CPU anymore for doing that job. That speeds up the access to GPU memory of a very remote GPU within a different node. A few more details on the configuration, but I think that'll be going into much more detail than necessary. Who's interested can request that information from me if needed. Then we're going to go into the more important part, the software. The hardware is one thing, but hardware without an infrastructure doesn't do anything. And that's why we designed DGX-1 as an appliance. An appliance means actually you unpack the DGX-1, you plug it into the electrical socket, you connect it to the internet, you switch it on, and the job is done. So the researcher doesn't have to install anything. He can get everything up and running within 10 minutes. And that is actually the whole concept behind the DGX-1 appliance. There's no need for any action in terms of installing software, updating software, implementing software. Everything is available right out of the box. And how that's done, I'll tell that on the next slides. So what do we actually deliver as prerequisite for doing the appliance approach? Well, first of all, underlying CUDA DNN, of course. That is the principal structure underlying each framework. Each framework used out there, Caffe, Torch, Theano, TensorFlow, and also other ones to come, use CUDA DNN right out of the box. So they are accelerated without you having to do anything else. Then we have a nickel library. The nickel library aids the programmers in doing multi-GPU applications, doing multi-GPU codes. Using our nickel library, the communication between the GPUs will be optimized. And you can use optimized functions without reinventing the wheel. And then, of course, our standard underlying mathematical functions, which you probably already know when you're doing a library replacement. So the QSparse, QBLAS, and QFFT, replacing the sparse, BLAS, and FFT mathematical libraries. Of course, you need them, and we are always further developing these routines also. To facilitate remote management and to facilitate deployment in an appliance approach needs a kind of virtualization, a kind of containerization. And that's actually what we do on the DGX-1. So we have an underlying OS, a base OS on the system, but all the frameworks and all the applications are containerized. And these containers will be deployed by us. We develop them, and everyone who procures a DGX-1, who purchases a DGX-1 and the support and maintenance subscription, will have access to all existing and future frameworks and containers. And we do that via a cloud management. So you actually connect to a cloud resource, and within this cloud resource, all these containers will be available. So DGX-1 and hardware is down here. We have a GPU-optimized Linux. It's an Ubuntu flavor, as far as I know. On top of that, of course, we have our NVIDIA drivers, so all our CUDA toolkits and all our libraries. We have an NV Docker. The NV Docker is a GPU-optimized version of Docker. If you want to virtualize a GPU, you will have to find a way of presenting this physical GPU as several virtual GPUs. And that's what's done by NV Docker. So the resource management has been optimized, but I think NV Docker is GPL, so that is open source as far as I know. On top of that, of course, are libraries, CUDA DNN and the Nickel library. And that is the basis for the actual applications or frameworks. So here we will be talking about the optimized deep learning frameworks, Caffe, Torch, Theano, and others. And we also offer a software which is called Digits. It's free of charge. And Digits is a GUI-based application which helps you design neural networks and train neural networks and visualize what is happening within your network. Is it converging? Which network design is performing better? If you have several network designs, you can train them in parallel, and then compare which network design is doing the best job. So that it is a very valuable tool for every researcher involved in deep learning, finding the best solution for his problem. And also visualizing what is happening within each layer of his framework. You will see what features is the framework learning. And if you're, for example, training in AlexNet, you will see that in one of these network layers, you will see features, edge detection. You will see features like horizontal lines, vertical lines, crossing lines. Those will be features the network will be learning by himself. And if you compare what the network is learning by himself in terms of features, you will see that it actually resembles 100% what those computer vision experts were doing 20 years ago, or for 20 years long. The neural network will be learning the same features by itself without anyone telling him to do so. But on the other hand, it shows that the experts in the past were doing the right thing, basically. Same thing applies to speech also. If you train neural nets with the raw wavelength, you will see that the neural net is learning features on various layers which resemble what the researchers were doing in the past with hand-coded routines. So they were going the right way, they're doing the right way. But it's very interesting to see that the network is learning features on its own without anybody telling him to do it, only based on the features he is learning. But you have to be careful. We now rely on two things only. We rely on design of the network. Is it correct or not? And we rely on the quality of the training data. Is it correct or not? And there are a lot of examples that networks are not learning what they are supposed to do. And there are a few interesting examples on that. I can, well, there's a nice story of the DARPA in the 80s of the last century. They were trying to improve the combat power of their main battle tanks. So what they actually wanted to do is implement a camera for the tank crew to be able to recognize disguised tanks, disguised enemy tanks. That was what they were trying to find a solution for. So the problem was, how do I recognize tanks disguised or camouflaged within wood? So the researchers came up with a very interesting idea. They said, hey, we're going to do a neural network design. They did that, and we're going to train it. But we need training data. So what they did then, they produced training data. They took 200 photos. Okay, it's only 200. It was in the 80s last century, so we were not talking about thousands and millions and billions of training data. 200 was sufficient. They took 200 pictures of battle tanks camouflaged within a forest. And then they took 200 pictures of forest only, without battle tank. And they said, okay, now we have enough training data, let's train our network. And they took 100 photos of the battle tanks disguised in the forest, and 100 photos of the battle tanks, of forest only, without battle tanks, trained their neural net, reached a trained network, and they used the remaining 100 photographs each to verify that the network was doing the right thing. So they trained, and then with the resulting photographs, they verified the results. And they received an accuracy of 94%. So 94% was a very high accuracy at that time, and said, hey, job done. Gave it back to the DARPA and said, you can now develop a product to help our tank crews. The DARPA said, okay, nice job, but we're going to prove it ourselves. So they took their own photographs, and then they fed it into the neural net, and they were receiving random output. no 94% accuracy. They were receiving random output. So sometimes the battle tank was being was being detected, sometimes not. But it was a random action. So they approached the researchers again and said, "What's going wrong? What is the problem?" Nobody knew. Until a deep learning expert had a look at the training data. And he said, "Hey guys, you trained the network, but not to detect battle tanks." The problem was the 200 photos of the battle tanks in the forest were taken on a cloudy day. The 200 pictures of the forest alone were taken on a sunny day. So actually, what did the network learn? It learned to distinguish good weather and bad weather. And it did that with 94% accuracy, but nothing else. Nothing else. And that is a huge problem. How do I verify that my network, my neural net, has actually learned what it was supposed to do? And there's another predominant example, and I think that went through the press also. Facebook trained the network to be able to detect people within an image. So it was able to detect, is there a human in my image or not? And after they trained the network, you as user had the possibility of uploading an image, and it would then detect what objects it would find. And then a guy from America, he uploaded an image, and Facebook neural net responded with, "This is a gorilla." So the neural net recognized a gorilla in the image. The problem was it wasn't a gorilla, his best friend was black. The problem was the network was only trained on white people. So the network always thought a human was white. Well, quite an uproar in the press and in all social media, of course. My friend is not a gorilla, my best friend is not a gorilla. So I think in the future, validity of training data sets will be a question which will have to be answered. Maybe there'll be standardized training data sets worldwide with percentage of training data representing the population of our planet. So a huge amount of them will be Asian, for example. Okay, yeah. But it is a huge problem. It is a huge problem. How do you validate that your network is performing the right thing? But we have a lot of researchers and labs working on exactly that problem. And it is not easy. It is not easy. Okay, let's get back to the DGX-1. Sorry for telling so many stories. Okay, let's skip this. This is marketing. I think the stories were more interesting than the marketing. Same thing here. Okay, software, 2 modes. Okay, it's fully supported software, base OS. Okay, what we actually do here is we have a repository of pre-configured frameworks, and we will be giving more and more framework support. So if customers come to NVIDIA and say, we're specifically looking at this or this framework, will you be able to support it? If we have enough customer requests to do it, then we will implement it, definitely. Cluster management, updates and security, everything is done remote. So there is actually no work to be done for a local administrator. Everything is done remotely. We do have customers who do not like this, of course. We have customers in, well, it's those customers doing cyber defense and cyber offense, for example. So all the defense guys, they don't like this because they're doing top secret things, but we have other ways of dealing with that then. But normally, in respect to a research lab, this is the way we do it. Everything is done remotely. No need to do anything on your own. The 4 steps, plug it in, and basically get working within 10 minutes. This is the way we do it. it's not a fully fetched approach like VMware. It's a very sleek approach based on Docker. You have a host OS. Okay, you always have the same host OS. You don't have the approach that you have various guest OSs. You will always be using an Ubuntu. But the nice thing is that because it's containerized, you have a full environment within that container, which is proven, which works. You can have various versions of CUDA, for example, within the various containers, always fitting to your application, always fitting to your framework. And that's the way we containerize all our applications, so that's really easy to get things running and to administer them. So container repository, you just select the containers you would like to use. We also have a job and batch management based on Mesos. So if you have not only a single DGX-1, but several, you have a farm of DGX-1s, and you have various containers which should be executed on this farm, then we have a job and batch management solution for supporting that. Okay, cloud management. This is the way you can then visualize what's going on, visualize the performance and what is happening within the DGX-1. Okay, maybe we only support NFS, so access to external storage is supported by NFS. The onboard or on-system 7 terabyte SSDs is a cache only, so it's only used for caching. It's not used for data. Data has to reside on a external device. Okay, everything's secure, of course. We use SSL and encrypted communication, so everyone having problems with external resources, cloud resources, or external administration, he can sleep well. Everything is fine in terms of security. Another picture depicting the total software stack, but I think that's repeating what we already said. Okay, marketing again. Okay, Andrew Eng from Baidu. He will also be one of the first users of DGX-1, and Baidu is heavily investing. And he actually depicts that deep learning and standard HPC will be growing together. He actually sees that they are converging. And with discussions I've had with CEOs of computing centers, they actually see the same thing. The departments and the institutes looking into deep learning now approach the central computing sites, and they ask for deep learning resources. And so they have to implement deep learning resources. And we actually see that deep learning and the standard HPC compute resources will converge in the future. And that is happening today already. Okay, another picture depicting that DGX-1 is actually in a league of its own in terms of performance. Here we have the normalized performance of a single Titan X, and in comparison, training various different frameworks, ResNet or AlexNet. You can see the speedups here, so the speedups are somewhere between 12 and 16 times faster. Okay, price is $129,000 US. We have a special education price for academic customers. But if you compare that, with what it replaces, you would need 250 standard servers to replace it. Then, of course, we're talking about other costs. The costs are even amount to about $2.5 million US if you compare that. So we're talking about a factor of 20. Less power too. So if you're using it for 3 years, actually it is normal that a larger HPC application, the initial cost you have for an HPC application, you will need the same amount for energy within 3 years. So the energy used within 3 years will be a similar invest as the initial hardware cost you had. University of Erlangen, for example, each 3 years they apply for a €2.5 million cluster, but they need €1 million on energy costs every year. So the energy cost is something we have to consider in the future if we compare different solutions. Then I think I'm finished with my DGX-1 presentation and happy to ask any questions if there are any. Thank you. No questions or information overflow? in terms of cost, $129,000. Top, at the top. Yes? Okay. Mm-hmm.
And usually in this phase, we can just squeeze every I/O out of system on our existing to Tesla per 1 CO.
Mm-hmm.
DGX-1 has really much more power and less I/O. So is DGX-1 also suited for this task? Have you solved that, or that's only for learning?
Okay. DGX-1 as deep learning appliance, of course, is mainly targeted toward the training phase, of course. This is, at the moment, is our only own product. You can see, or you will see products coming from our OEMs beginning of next year. And there you will have various CPU-GPU ratio possibilities, of course. Here we now have a 2 CPU, 8 GPU, or, well, actually it's a one CPU, 4 GPU setup, which is loosely connected. 2 of them loosely connected. It's not fully symmetric. But if you were looking at other ratios, you just spoke about a ratio of 1 to 2, where you need a lot of I/O performance to feed your GPU resources, then of course you could think of different solutions upcoming from our OEMs, and they are working on 2, 4, and 8 GPU designs also. Then maybe the pre-processing stage would be better done on a system which is more suited for that, and I would even think of maybe a power-based system, because the power CPU has the advantage that it uses NVLink to interconnect with the GPUs, which gives you a much higher bandwidth than an x86-based system. And IBM, for example, announced the Minsky system, and that is, it actually has two CPUs in it and 4 GPUs, but it's actually a 1 CPU, 2 GPU setup, and 2 of them in a single system. Maybe that would fit better in the pre-processing phase. Yeah, and I think we should just maybe have the possibility of benchmarking various systems in terms of comparing performance levels. Yes? Okay. Yeah. Okay. We will have to go into a little bit further detail on that. And the reason for that is in the implementation we have at the moment, we still rely on PCI Express. But PCI Express is not used for the actual transfer of data, but it is used for signaling. So the setup latency at the moment with Pascal is actually the same as with a PCI Express-based system. The performance upgrade comes from the not the initial setup of communication, but the actual transport of data. If you're doing small chunks of data, then you're not using the NVLink capability in terms of performance at the moment, because you will always need the PCI Express as a signaling bus. So it would be better to maybe rethink the algorithms so that it is limited to few using high data transport than several using small data chunks. That will vanish with Volta, because within Volta we're not going to be using the PCI Express for signaling anymore. That will also be done via NVLink. NVLink is only a transport mechanism at the moment, but not a communication mechanism used for setup. Any other questions? Yes? No. Okay, good question. Well, first of all, we're mainly responsible for giving you the tools. So mainly giving you the hammer. What you do with the hammer is then your thing. So the low-level implementations of optimized libraries, etc., CUDA, DNN, and so on, that is actually done by our engineers. But they work closely, very closely together with all developers out there in terms of frameworks, etc. So there is a huge interaction within the community developing further. And there are various tasks which are heavily discussable. For example, if you want to train a single network, not only on one GPU, but on several GPUs. So you would like to scale using several GPUs, but training only one network, not training several networks in parallel, training one network, which is very large, and distributing that on various GPUs. Who is responsible for that? Is it the responsibility of the guys doing the CUDA libraries? Or is it the responsibility of the overlaying framework? which has more information at hand and maybe even do it better than the guys doing the low-level function calls. So there has to be a close relationship between the low-level programming of a library and the framework relying on these libraries. We actually do that very closely. So and in most times, the agreement is that it's actually the framework which is responsible for the distribution within. But we deliver the underlying libraries, so the CUDA DNN and the NICL library for optimized communication between the GPUs. But we have to interact, of course, yes. Okay, I think that heavily depends on the relationships of the developers within each community. We try to work with all of them, yes, as good as we can, yeah. Yeah. Okay, but there's another aspect. To actually further develop solutions, we have now introduced a new initiative, and this initiative is called NVAIL, and NVAIL is the abbreviation for NVIDIA AI Lab. And we have now nominated 2 leading institutes in Europe who have been nominated as NVAIL. It's the ITSIA Lab, headed by Jürgen Schmidhuber and his colleagues, who are responsible for developing RNNs and LSTMs, for example. And the second institute which has been nominated is the DFKI, Deutsche Forschungszentrum für Künstliche Intelligenz, so German Research Center for Artificial Intelligence, based in Kaiserslautern. They have about 800 researchers, and they've been nominated too. And I know they have a close cooperation with the University of Prague. But I think you know more on that, which institute that is. I think it went through the press because Angela Merkel was here in Prague, and they signed documents. So I suppose I'm going to be here more often in Prague to help that cooperation with the FKI. But I like Prague, so I'm going to come here. Yes, I think you had a question. Yeah. Mm-hmm. Well, okay, yeah, right. Okay, my personal opinion, and this is maybe not depicting the official opinion of NVIDIA. So I'm going to take all my green stuff off now. No, better not do that. We have women in the audience. Okay, okay. So basically, I think that in terms of deep learning, in terms of training, in terms of inference, of course, specialized solutions and specialized hardware will always be out there and always be developed, which have a higher performance, of course. But in the end, it's always a question of economics. In the end, it's always a question, how expensive is that going to be? How high is the number of units I'm going to sell worldwide? We always, when we develop a new architecture, we develop Pascal, but we have to develop this architecture in respect to all fields we are working in. Pascal architecture will be used in consumer boards, so we have to please all those gamers out there. They want to see their games in 4K, high resolution, 60 frames per second, high resolution textures on their first-person shooters or whatever. We have to please them. They are the largest number we are trying to please, to be honest, and they are paying a lot of money for that. So, and we have over 90% market share. Okay, that's something else. Then we have to please all those cut designers out there with our Quadro line of cards. They're looking into other features. They're looking into stability. They're looking into certified drivers supporting their AutoCAD and CATIA and whatever applications. So they're looking into stability, not price. They're paying thousands of euros for a single board, but they want the stability because they're developing cars which sell for 100K euros or even higher. Then we have to please all the HPC guys out there. They want to do computing. And then we have to please all the embedded guys out there. They're not doing high-end computing. They're looking at energy consumption, power efficiency. And we have to do that with a single architecture. So there's always a kind of trade-off between all all those groups of users we have. We have to find a common denominator for everything, which is not always easy. But that means that we're not always developing in respect to a single field of application. We have to have a common architecture for all. But the advantage is we have a common architecture for all. We have a common software development for all, and we have lower cost because we only have to implement one architecture. Of course, others will implement some TPUs like Google, for example, but I don't think they're doing any more work on it since they saw the new performance numbers of our GPUs. It is always a trade-off, but in the end, economics will speak. Will be the main argument in terms of adoption in the field or not. That's my personal opinion. It's good that people are working on other things, of course, and I do think that research done, for example, in the region of the Human Brain Project may have effects in future GPU and CPU designs, of course. If we understand how our brain works, and we are still factor 100,000 far off of the human brain in terms of energy efficiency. The human brain we know which computing power it has, and it consumes about 10 watts of power. And we are still factor 100,000 off. So we have a long way to go.